before we get started with that, there's a couple announcements, and we're going to do trivia. So if you do want to play trivia, but you haven't gotten a trivia sheet and golf pencil yet, you can come up to the front and grab one now while I'm talking. So I guess just a few announcements, bookkeeping. First thing is next month, Astronomy on Tap will be on March 26th. The next announcement is that in April, you've probably seen this on the social media, but we're doing a public lecture series at the University of Washington for astrobiology. We're bringing back some really cool alumni of the program, including Giada Arney, who's the interim project scientist for HWO, and Ken Williford, who was the deputy project scientist for the Mars 2020 Perseverance rover. So it should be a really interesting series of talks. They're completely free, but you do have to register. But we'd love to see all of you there. So, okay, you can't hear me? Can you? Oh, okay, sorry. I couldn't tell if the hand motions were for me or for somebody else, sorry. Okay, yes, so please come to these. We'd really love to see everyone there. And then the other announcement is, as you know, last month we started a fundraiser to try and get money so that we can get a projector before the sunlight comes out again and we can't see any of the talks. So I just want to give you an update. Like, that's going super well. As you can see, as of tonight, we've raised like $1,200. Yeah. Thank you all so much. So I did some work, right? Some research. That's what I do. Into projectors. And as it turns out, projectors are incredibly complicated. And I was finding projectors where it was like, this should be fine, and they were like $500. And then I was seeing other sites that were like, no, you have to get this. And it was like $10,000. So I decided that for so many reasons, I needed professional help. So what I'm going to do is this month, I'm going to try and reach out to an actual company now that we have some sort of budget and see what they would sort of recommend. So I just want to give you an update on how that's going. The fundraiser is still open, and then hopefully we'll get an idea of, if we have enough, if we're good to go, or if I need to look for some other avenues of funding as well. So that's the update. And with that, we're going to get started on trivia. So for anybody who has not played trivia with us before, I'll just give you a quick rundown of how it's going to go. I am going to put up each question on the screen for 30 seconds apiece. In that time, you will, write down your answer on the trivia sheet with the golf pencil that we gave you. And then at the very end, I will go back through all 10 questions, but the second time it'll only be for 15 seconds apiece. But you get 2 opportunities to get your answer down. And then we will have everybody come turn in their trivia sheets before we start the first talk. Okay, so with that, does everybody feel ready to play trivia? Awesome. Oh, so enthusiastic. All right, let's get started. Hours ago.
Trivia sheets were 0 indexed, so this is question 0. Just go from the top down. Thank you.
first pass through. I'm going to go all the way back through, and we'll look at each question for 15 seconds apiece this time. And yeah, the sheets are 0 indexed. I just slipped my mind, but just go from the top to the bottom. So 0 is 1, 1 is 2, 2 is 3. It's a fun little puzzle for you.
It's a brain teaser.
Yeah.
Yeah, I was figuring with the 5 in the month, I was like, just like which one you like. It wasn't 2 nights ago. No, because it's 16. You know what I mean?
Hopefully you got all your answers down. You can bring your trivia sheets and golf pencils up to us at the front now. Please don't forget the golf pencils. Please, please, please don't forget the golf pencils. Okay, at this time, it is my pleasure to introduce the first speaker of the evening. It would be my pleasure to introduce him. I would love to introduce him. Can I introduce him to you guys? Thank you. Thank you. Okay. So I was told explicitly by the speaker that I had to do it like this. So right now I'm bringing up Andy Tzanidakis. Say his last name. He's a Ph.D. candidate at the University of Washington's Astronomy department, and he works on the weirdest stars in the galaxy. So with that, I will bring up Andy to tell us about when stars go dark.
All right, I'm gonna take this off over here if that's all right. Can everyone in the back hear me all right? Give me a thumbs up. Okay, excellent. Well, it's great to see everybody. I am Andy T. We're going to be talking about the weirdest stars in the Milky Way galaxy. And I'm going to be particularly talking about just one star. And you might be asking me, like, why are we going to talk for like the next 25 minutes or so about one star? And as a star lover myself, it turns out that stars are a lot in the Milky Way galaxy. Now here's a cool animation showing you a field, just a random patch of the Milky Way galaxy, and you can see that stars are everywhere. Now, as someone who studies stars for their PhD, I can tell you that this is one of the most boring images of stars, and that's because these pictures often depict stars as these static objects. But what's really fascinating is that stars actually change with time. And today we're going to be talking about a story about how stars change in time, and specifically how their brightnesses change over time. And this story is very intriguing. So in order for us to talk about this topic in the first place, I'm going to have to do a very difficult task and make you all into experts of stellar variability. Now, it's not that bad as it sounds, but here we go. So we have two flavors of stellar variability. And you know, every time I show this, people get very confused why I put an ice cream cone with a star. So we have the intrinsic stellar variability that I'll be talking about, that is intrinsic to the star's properties. And then we have the extrinsic properties, so things that are outside of the star's environment that can contribute to its brightness. So let's start with the first one. So intrinsic, what does that mean? So the star, our sun, which is a star, is a middle-aged star. So we usually call these main sequence stars. And what that typically means is that in the core of the star, you have fusion between elements. So specifically, hydrogen converts into helium. And this is really important because with the high pressures and high temperatures, this allows to happen. And when the fusion occurs in the core of the sun, you essentially get energy that's being radiated outwards and what makes the stars shine. Now, all that energy is pushing the star outwards, but we have to remember that the sun is about 300,000 times more massive than the Earth. So it's this enormous sphere, and it wants to collapse under its own weight. So it turns out that when you are in the main sequence, you are in what we call a hydrostatic equilibrium, meaning that the two forces between the energy of the star that's fusing elements together and the gravitational potential, which is trying to squish the star together, is perfectly balanced. And this is a pretty big deal because it turns out that when these two forces are balanced, that the star actually remains perfectly it has the same size, the same brightness, and it doesn't change. So, when you wake up, you'll see the sun roughly at the same brightness as you would from one day to the other. Now, of course, I lied a little bit. The sun does change its brightness ever so slightly. So if you have a really powerful telescope, you can actually see these, what we call convection cells. So these are kind of like these hot plasma blobs that are rising to the surface of the sun and are falling down because they're cooling. And every one of these are like, the size of like maybe the state of Texas or something like that. So, humongous convection cells. So if you were to look at the sun on a very small scale, you would see very small brightness changes. Now, when we look into the Milky Way galaxy, we see that there are millions, if not billions of stars that are constantly changing brightness. So here's a real image actually in the M33 galaxy. And you could see this is like about a couple of hours. And you can see there's like a bunch of these stars that are flickering. And it turns out that some of these stars are actually not like the sun. They're a little bit more evolved. So now they're converting maybe helium into other elements in their cores. And so as a result, they're actually pulsating. So here's an animation showing you, when they're expanding, they're cooling down, and then when they're contracting, they're heating up. And so when we look at their light curve, is what will be over here, which is the brightness over time, we could see that the light curve, it has kind of like this pattern that almost looks like a perfect sine wave over here. Now this is really cool because we can actually kind of see roughly the same similar behavior in the night sky. If some of you have seen the Orion constellation, which was in the trivia, by the way, there are stars like Betelgeuse, which are red supergiants. So these are now enormous stars. They're very cold. And so here's a simulation over here on the top left that's showing you what these convection cells look like. So these blobs that are coming in and out of our view are making the star vary in brightness. So this is all intrinsic variability. So that all has to do with just the properties of the stars themselves. Now there's another, which is the extrinsic properties. So the things that are around stars that can cause and contribute to the brightness changes. So the first example is something that maybe some of you have heard about, exoplanets. So here we have a star, and we will make a planet pass in front of it. And you can see on the top right, we have a brightness curve, so light curve. And we could see that when the planet passes in front of us and the star will suddenly dip for maybe a couple of hours and then come back to its nominal brightness. And this happens over the course of just a few hours. Now, I want you to remember very specifically this U shape because we're going to come back to this. This is a really important shape to remember. Now, it turns out because planets are round, or spheres, I should say, we get this really nice symmetrical looking light curve. Now, here's another thing that you need to remember is that the size matters of the planet compared to the star. So when a planet passes in front of a star, the ratio between the planet and the star will determine how deep that dip that we saw in the light curve is. So you have a bigger planet, it's obscuring more area of that star, and so you would see a bigger dip, whereas the small one, you get the opposite. Now, here I love to show this. Can I get a raised hand on how many people see one planet? Okay. I would be very concerned if you couldn't see one planet. Okay. How about two planets? Peter raised his hand. Oh, can you not see it? Well, it's tiny. I was trying to trick you. Well, the reason why I bring this up is because there's actually a limit to when we're looking for planets around other stars of how small that planet could be compared to the star. So obviously, things that are really, really, really small are going to be really impossible to see. So of course, there's a sweet spot here, depending on the sizes of the planet and the star. Okay. Now, there are not only planets that go around stars. There's other stars going around stars, and we call these binary stars. And so here is showing you, again, a light curve of a binary star, where now you have maybe one star that might be a little bit more brighter than the other. And when they're passing in front of each other, you will see these sudden dips in the brightness over here. And depending on which one's passing in front, will cause a big one and a small one. And what's important to remember here is that this is a very periodic behavior, meaning that because they're going around each other, we will always see these dips happening at a fixed time interval. That's, of course, assuming that there's no other intervening forces that would make this happen. Okay, so there's a lot here. So when we talk about intrinsic and extrinsic stellar variability, there's this diagram over here, which is called the stellar variability tree. And essentially, you can't really see all the names, and it's it's kind of hard, but essentially, there's a lot of classes. And even though this diagram here was back from 2018, this has been out of date for years now. And the reason for that is because approximately, I would say, every 6 months or so, astronomers are constantly finding things in the night sky that are, changing with brightness that are a new class of variables. And that's because we're building better and more sensitive telescopes that are helping us discover some of these incredible changing stars. Okay, so now I want you to really appreciate this problem because in the Milky Way galaxy, we have about 300 billion stars or so. That's the current estimate. And here's a beautiful image taken from pan stars, and we're just zooming into just, again, one small patch. And now, because you have learned a little bit about the stellar variability, every second to every minute, to every hour, to what we'll be talking about in a bit, going to centuries, these stars are constantly changing with brightness. And this is a really difficult question. So if you're like, wow, this is very overwhelming, I would agree with you. This is a really hard problem in astronomy in trying to figure out what all the stars are doing and how can we find the ones that are most important. So now we're going to get into the story of this really strange star. And our story starts back in 2009 when NASA had launched what I think is one of the most important telescopes in human history. It's called the Kepler Space Telescope. It was named after Johannes Kepler. And the Kepler Space Telescope had basically one mission. It was meant to find planets around other stars, and specifically habitable planets and other stars in the habitable zone. So Kepler was basically staring at one patch of the night sky in the constellation of Cygnus for over 4 years. It was basically an unblinking eye for 4 years. And the reason why you want to do that is if you remember that diagram that we're looking at for when planets pass in front of stars, we could see that you want to make sure that you're always staring at the stars so you could see those blips. So this is the Cygnus field. Kepler observed something about 200,000 stars. And over the course of its mission, it discovered something like 2,000 exoplanets, which is incredible to think about. So here is one of the images that Kepler took, and you could just really take it in all in. So all of these stars that you see here, probably the majority of them will have planets around them. Now, at the time when NASA had launched this mission and we were producing all of these light curves to investigate these stars, we needed the contribution from citizen scientists, actually, to look through the data and try to figure out if we can find any planets. And so around 2014, there was a paper that came out by Professor Tabitha Boyajian. And they titled it as Planet Hunters, which is the name of the project that was trying to look for these planets. And they gave it this weird name, KIC A462852, which is just an astronomy phone number for a star. It's nothing too fancy. But more specifically, the title was, Where's the Flux? And if you could see the acronym to that, WTF, which I think is one of the greatest titles for a paper that has such high importance. So this is the star that we're going to be talking about. It's called often referring it to as Tabby star or Boyajian star. It's named after the main discoverer, Professor Tabitha Boyajian. So right here, you could see an image of this star over here, and we're going to be talking about why this star was so weird when Kepler observed it. So here we could see one of the brightness curves, the light curve that we saw from Kepler. And over here is the whole light curve history that Kepler saw over the 4 years. And if we zoom in to specifically to these bits where the star is doing these weird patterns. So you might notice that the star is constant in brightness. And then suddenly, just out of nowhere, the star seems to be going completely bananas. So look at these diagrams down here. You could see that these are all brightness reductions. And specifically, I want you to pay extra attention to the shapes of these dimmings. Now, if you remember the diagram we looked at when planets pass in front of stars, you see a really nice U shape. These don't look like U shapes, right? And this was really, 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 really strange at the time. We have no idea what could produce these sort of shapes of objects passing in front of stars to make these sort of transits. More specifically, just for context, right, when a planet passes in front of a star, you usually see about like 0.001% of the star changing in brightness. This is about 20% in change, right? So this means that it must be something really big. And also these events, last for maybe about like 10 or 15 days. So this was super strange. When they found this, everyone was like, WTF, for real? Like that was really the reaction from the community. Now I'm about to do something that astronomers should not be doing. Has everyone here seen Contact? Raise your hand. Okay, the majority of you. Okay, if I had to summarize Contact, it would be Jodie Foster discovers aliens, but I think it turns out to be her dad, but then it's not. But the most iconic thing about this film is Jodie sitting near the VLA and using these headphones that you can't see here, and see this really dramatic shot of her listening, trying to find aliens. Now, I am on live stream, and I'm going to make this very clear because I'm being recorded. This is not how we do astronomy. This is very important. I'm going to say it again. This is not how we do astronomy. Now, why am I showing this to you is because way back in 2000 and, I don't know, maybe 5 years ago, I made this cool project where I tried to sonify the light curve of Tabby star. So what you're going to hear, I don't know if it's going to play once I click it, is I've translated the brightness of the star into a pitch. And what I really want from this is you to just really appreciate how the star was, constant in brightness and just suddenly decided to, change in brightness. So I'm going to play it, and hopefully we hear something. It's going to not be a really particularly pleasing sound. I'm going to give for it. So there's one bit where it, decided to go completely crazy. This one here is called, this one's called the Batman because it kind of looks like Batman. I don't know. I've seen people talk about that one. Okay, here's another wild one. Yeah, and then it just comes back to normal, which is super weird. And then this one over here. So there you go. Okay, so now you've heard for the first time what Tabby star might sound like in sound. And of course, again, this is not how we do science, but this gives you an appreciation to generally how those weird shapes can make those those steepness and brightnesses that are changing and could be super strange. Now, in reality, this is kind of like me. This is how really science is done, right? You're looking at your computer and you're like, what the fuck, for real, nobody knows what's going on, and this is really what represents what was happening with Tabby star. Okay, so we've seen the brightness changes in Kepler. This was a huge deal. Now, the main question that we wanted to figure out was, did these dips happen at any other times besides when Kepler saw them? Kepler saw them back in 2012, and the question is if we could find those dips in other telescopes. So there's this really cool project that started back in the early, towards the early 20th century, late 19th century, where basically it's called the Digital Access to a Sky Century at Harvard. And essentially what this is back in the early 20th century, Harvard was leading this huge effort to basically collect photographic plates of the night sky. And the idea was that back then they were even thinking that, wow, it'd be super useful to have like an atlas of the sky and being able to kind of go back and look at the archives of these stars and really trying to understand their properties. And a lot of this effort was actually led by incredible female scientists. Over here you could see there's Annie Jubb Cannon, Henrietta Swan-Leavitt, and many more prominent scientists that were leading a lot of these efforts and were kind of the most important discoveries for stellar astrophysics at the time. But what's really cool is that this project, DASH, has about 500,000 photographic plates of stars going back all the way to the 1800s, which is pretty incredible. So Bradley Schaefer, who is a professor at Louisiana State University, came out with this paper quickly after the original discovery of the Tabby star came out. And the title was that the Boyajian star faded on an average magnitude rate of about 0.16, that's about like 0.2 magnitudes per century from 1890 to 1989. This change in magnitudes, maybe you don't speak magnitudes, and you probably shouldn't, is about a reduction in brightness, about 16%. Okay, that's a pretty big deal, right? Like if you were to go out and see the sun change by 16%, that would be noticeable to the naked eye. So this was a huge claim that he had made. And basically, he went back to these photographic plates and was like, look, like I could see it there, basically. Well, you know, he did more than that. And he basically stitched together all these images and measured the brightness of the Boyajian star. And what he found was that actually, yeah, true. Like the star was actually becoming fainter and fainter over the course of those years that they were observing these photographic plates. And this was pretty crazy because no one had ever seen a star do this before. Now, the astronomical community went crazy. You know, there was a lot of pushback from this because people just simply did not believe it. In fact, Michael Hipke went back to photographic plates that were taken from a telescope in Russia around the same times that, you know, they just happened to be pointing at that part of the sky. And they went and extracted the brightness measurements of the Tabby star. And what they found was actually that they could not find that dimming that they had claimed, that, you know, that century-long dimming. And, you know, this was something that the community was like, yeah, we're sure that probably Bradley had made an error in his measurements. There's no way that a star, you know, over the course of a century would become so faint because really the astrophysics is basically unknown of what could be causing that. But then Ben Monet and Joshua Simon, what they did was they took all of the brightness measurements measured from Kepler, and over the 4 years of Kepler, they noticed actually the star was dimming, which was wild. So we went back to the theory of like, oh, okay, the star is fading. And in fact, over the course of the 4 years that Kepler observed it, this star did drop by 3% in brightness. Now here you could see what the brightness, the light curve looks like, and you could see that for basically 3/4 of Kepler when it was observing it, the star had a really linear decline, and then basically it decided to do something way more drastic, and it seemed to be getting fainter faster. So this is about a 3% change in brightness. You know, they did a really thorough job to make sure that this was not an artifact of the data. So, for example, they looked for other stars in the region to see if, you know, if they were changing brightness. They also checked to see if stars that are like the Tabby star change in brightness, and they didn't find any of that. So this is a really unique star in the sense that this was the only star that we knew from Kepler that had this property. So, okay, now we have to talk about what's going on here. Now, there's a lot of papers out there. There's like something like maybe like 100 papers of people really trying to add to the complexity of this problem. So as far as we know, the Tabby star is a main sequence star. It's a hotter version of our sun. It's an F-type star. And what that means is then that basically we think that it's a middle-aged star. So one of the main suspicions that astronomers had at the time was that this certainly must actually be dust around a star. And, you know, feel free to ask me in the questions about dust around stars. It turns out this is a little bit of a complicated problem, but basically there could be some dust left over when stars are being created, and that dust sometimes can pass between us and the star and block some of its view. And when we took the most sensitive telescopes that we have, going from the optical wavelengths where you and I could see to radio and submillimeter, basically there was nothing there. This diagram basically here is showing that as we go into further and further wavelengths, longer wavelengths, basically there's nothing there. There were no detections there. And the detection that they were able to basically make is that if there is dust there, it must be at least 1/1,000,000th of an Earth mass in terms of masses around the star, which is kind of the equivalent of basically like a large asteroid. And here you can see one of these images, and basically they couldn't find anything. So not a particular piece of evidence to point to the fact that this was dust. Now, I am going to contradict myself and say that back in 2016, Tabby and her team actually did find other dips in the Boyajian star, and what they were able to do is measure the dips as a function of wavelength. So it turns out that if material is passing in front of us, if you're looking at it with different wavelengths, when the dips are deeper in the sort of shorter wavelengths, that means that dust, that material is absorbing more of that light. And it's the opposite for things that are in longer wavelengths. And so what they found was that there's this dependence on the wavelengths and these dips. So this seemed to suggest that there was actually dust, even though we just said that other telescopes didn't see this dust. So there's this back and forth contradictory evidence to point to the fact that the material that's passing in front of it could be dust. So they claim that it was dust, even though it's still an open question, really. And there were some other telescopes using the UV to also make these measurements, and basically they kind of found the same picture, that it must be produced by dust. Now, some other wild theories are out there. So, for example, there is this theory here, which suggests that the system actually has a planet that's almost the equivalent of Saturn, and it has two clouds of what we call Trojan asteroid-like clouds. So you can almost imagine them as like this, this clump of asteroids that are leading and trailing the planet. And what was really cool is that you could see here this ring-like figure is basically the light curve of Tabby star, and they can kind of explain how these dips would correspond to this. And this was back in 2017, and they had made some predictions that early in 2021 we would basically see this whole thing repeat itself. Did that happen? No. Well, it was a good take. It made a really nice figure, which I love always showing. So it's a good theory, but of course the fact that we haven't seen it happen again is super strange. Though I will make a point here and show you that here's a cool animation that I made of what happens when you take a planet that has these massive rings and you pass them in front of a star. You can essentially get these light curves that you're going to see over here, where the star, will get really faint, but then it'll actually get slightly brighter, and then slightly fainter, and then bright again. And that's because some rings around planets, specifically like Saturn, there might be gaps in the rings that might be carved by different moons that are in Saturn's orbits. So you can get these really funky shapes. So this could be a potential scenario where some of those weird shapes that we're seeing are actually produced by something that looks like a disk, and that could produce these kind of really strange looking transits. Another theory is this cloud of asteroids that is on this highly elliptical orbit that seems to be passing around Tabby star every once in a while, but it's not entirely periodic. And basically, they require something like 100 asteroids grouped together passing by Tabby star. And when they're passing by, they're doing it so fast that they're actually not heating up. And that's why we cannot see them in the infrared light. And they're able to basically reproduce some of these dips, even though they kind of look okay-ish in my opinion. But there's a huge issue with this picture in that when it comes to modeling a lot of these light curves, often when we induce more and more bodies, it of course becomes a lot easier to explain something like this. And so there's a trade-off in how we choose really complicated models to explain some of these events and what's really happening in reality. Now, we've seen something like this actually happen in our own solar system. For those who were around in 1994, you might remember Shoemaker Levy 9, when this comet basically crashed into Jupiter. So there's this comet, and it basically got really close to Jupiter, and Jupiter's tidal forces actually stripped it apart. And there's this beautiful animation where you could see a Hubble image of where the comet actually fell onto Jupiter. And it created this huge flash show on Jupiter, but essentially it created this, this cloud of debris of material that was going around Jupiter. So we have seen that, though we don't know exactly how often this happens. Another crazy theory is that the Tabby star actually ate another planet. And this is actually something that we know happens quite frequently around stars. And so one of the theories was that the Tabby star actually had engulfed a smaller planet. Specifically, they think it was probably like an icy moon. And when you're a star and you've just ingested a planet, you're probably not going to feel too well. You're going to be like, my tummy hurts or something like that. And so basically what they did is that they used computer models to predict what the brightness change would be of that star over time. And so these diagrams here show you basically that you have a bigger and bigger body, the star would take a much longer time to basically settle into its new equilibrium position. And this is the only theory that we know so far that actually seems to be somewhat consistent with that longer sort of declining brightness that we saw. It really can't explain why we're seeing those shorter brightness variations. My other favorite scenario, and it seems like it's the internet's favorite scenario, is of course the one and only topic, aliens. Feel free to Google it. It's probably the first thing that you'll see. Yes, aliens could be a thing. Now, in all seriousness, Tabby Star did really puzzle us, and astronomers were actually serious. They were like, okay, like what are the odds that this is actually an alien? So several groups had pointed radio telescopes to see if the Tabby Star was actually beaconing any radio signals to us. And, it comes to no shock that obviously they did not. Everyone was crying and it was sad. But, I think that it makes it even more puzzling, right? Because, okay, if it's not aliens, then what the heck is it, right? There's a lot of ambiguity here, but definitely not aliens. By the way, this is here a theoretical Dyson sphere. Some people think that, it could be possible that aliens could build these structures around stars and they can make them disappear for over time. This is a real search, and this is something that we should pay attention to, but unfortunately was not the case for Tabby Star. So future directions. I've talked about a lot of papers here and a lot of evidence that seems to contradict itself. The reality is that when you look at the literature almost 10 years later, the evidence does not seem to be conclusive yet. So Tabitha Boyajian and her team are actually just submitted a proposal to observe Tabby Star with the James Webb Space Telescope that Gourav is going to tell us about. This is the state-of-the-art telescope, and hopefully it could tell us a little bit more about what's going on with the star, specifically looking in the longer infrared wavelengths. Today, during my research group meeting, we actually pulled up one of the brightness, the light curves of Tabby Star. This was as of 2024, back in September. And the star is basically chilling. It's not doing anything. That's kind of like the weird part here. So nothing dramatic has happened. Of course, we're keeping an eye on it because if something happens, we definitely want to keep all eyes on it. There is a website, if you're so passionate about this topic like I am, if you go to where'stheflux.com, it will basically give you, an update on what's going on with Tabby Star. Most of the days it's going to be not much, and when Tabby Star decides to go bonkers again, you will know about it. Tabby will blast out again an announcement to the community to let you know where it is. But I love this is probably the only star in currently that we know of that has a whole website dedicated to itself. So Tabby Star is truly a unique mystery, and I think one question that really fascinates me is the fact that out of all of the 200,000 stars that Kepler saw, this was only one star that we saw doing this, and that is super strange. I think that in itself is an even bigger mystery. Because this points to the fact that this mechanism, that whatever's producing these brightness variations, must be so phenomenally rare. As far as we could tell, it's like something in about like 1 in a million at least. So together with some of my collaborators at the University of Washington, we are leading one of the first ever large experiments using telescopes both from the ground and the space to look for these elusive Tabby stars, these Boyajian stars that look very similar. And I'm really happy to report, and soon this paper will be published, that we have actually found quite a few. Not as many. We're finding something about like 1 in a million. And so here's one of those light curves that we have found here on the bottom. And here's a light curve that was seen from Kepler. So very similar to what the Tabby Star looks like, except for the fact that the one at the bottom is basically like over a year worth of dimming and a 75% dip, whereas poor Kepler saw something that was like 20 days. So a much bigger event. But this points to the fact that maybe these things are actually happening on much larger scales. As far as we could tell, we've pointed telescopes at these stars. They seem to be pretty normal, just like the Tabby Star, which makes it even more puzzling. So believe it or not, I've dedicated almost half of my PhD time working on this project. And so I'm happy to see that there at least there's other stars like it, which means that perhaps this is a mechanism that we can pinpoint at one point. And we're super lucky because now we'll have many more telescopes to our disposal to look for these unique tabby stars. So thank you all so much. Feel free to send me an email, or if you have any questions, I'm happy to take any questions. And again, thank you all so much for your time. Okay, questions? Yes, please.
Is it possible that it's not just one phenomenon that causes that, but actually a combination of multiple effects?
Yeah, so the question is it possible that instead of just one phenomenon causing all the dips, if these can all be separate events? That is really true. And actually, a lot of people have entertained that idea. The problem is that the small dips that we're seeing, we can actually do a decent job in explaining them, but that longer dip seems to be the one that models often really fail to explain. One theory was that basically there is this intervening material between us and the tabby star, which is about I think it's like 2,000 light years from us, where there's this really diffuse sheet of material that's passing in front of us and the star, and so it's making it fade over that time. But that theory was quickly disproved because we basically were able to measure, how much stuff is between us and the star, and we didn't see any variation. So it could be. These two events don't need to be dependent on each other, but it seems really strange to me that this is the only F-type star that we know of that's doing this, and all of the other stars that are of similar category don't seem to be doing this. So this is still an investigation that I think needs a little bit more attention. Great question. Yeah, right here.
For the dust theory that you talked about,
Yeah.
why would that affect other stars nearby that it's looking at, like if it was something?
Yeah. That was, so the question was, for the dust theory of a material passing in front of us, why wouldn't that affect any other neighboring stars? And that's actually what the scientists did. So this is a great line of thought. And we didn't see the stars do that. So that's one reason why we're like, okay, that's weird that if that material of dust was only isolated to that star. So we think that's not the theory because we saw other stars around it, and they didn't do that. So it seems that that might not be the case then. Yeah, right over here. Yeah.
Statistically, our systems in, say, the Milky Way, the Milky Way plane,
Mm-hmm.
and then as you're observing with some of these time frames, how do you distinguish between the plane of that system maybe rotating away?
Mm-hmm. So the question here that I'm getting, if I understand correctly, is so when we're viewing this, we're seeing it kind of like edge on, right? So the material is passing in front of us, and you're asking if the plane of that changes at all. So like.
Well, first, statistically in systems in our solar system, do they tend to be edge on?
Oh, okay, yeah. Yeah. So there's no preferential direction for viewing systems hedge on. So like that could just be like a random orientation. So clearly the things that pass in front of, like planets passing in front of stars, will have a preferential direction where we can actually see that. But the things that are not, are just basically simply invincible for us to see. And then your second question. Do systems rotate? That's a really good question. So if the inclination, so the plane of which this material is rotating, must be rotating. We don't think so. And the reason is because when that usually happens, there needs to be a really massive planet or body in that system to make those rotations happen. So for the Tabby star, we haven't seen any planets in the first place. So we don't really think there's anything to cause these sort of changes. So as far as we could tell, its plane is fairly constant. Yeah, it's a good thought. Yeah, we have one here. How close is this to our solar system? Oh, yeah. Okay, that's a great question. So could it be that this material that's causing this dimming is in our own solar system. This is pretty cool. Uranus's rings were actually discovered when we were looking at other stars and we suddenly saw them disappear for a second. And it turns out that the rings were actually blocking a little bit of that light. We did that check. And as far as we could tell, it was not close to any planets or any material that's in our solar system. And the issue with that theory is that we would see other stars do that as well. Again, the fact that it would be very isolated to just one star and we've only seen it once is really troublesome in this scenario. So basically, the fact that, it couldn't be that it's only producing one star to cause these depths. It would need something to be much bigger. Okay, let's do one or two more questions. Yeah, Sean, go for it. Yeah.
Also had a dimming in 2019. Did we ever figure out what caused that dimming?
In Tabby Star?
Betelgeuse.
Oh, in Betelgeuse, yeah. So the dimming in Betelgeuse, yeah, I had a slide where Betelgeuse changed brightness. So Betelgeuse is a red supergiant. So this is not a main sequence star. And Betelgeuse back in 2019, right around COVID, had this crazy dimming event. Basically, it was like a few magnitudes at least. And it was noticeable actually with the naked eye. What we think happened to Betelgeuse is that it burped. Supergiant stars like to burp a lot because they're big and puffy. And it actually produced like a little plume of dust. And it obscured itself. I call it like a star burp. So that was the cause for Betelgeuse. For Tabby Star, we don't think that F-type main sequence stars burp. Like that would be like one of a kind. Main sequence stars should not do that because again they're under this hydrostatic equilibrium. So they're fairly static in that sense. Okay, I could take maybe a last question. Yeah, all the way in the back.
You probably don't have it for Tabby Star, but
Yeah.
spectroscopy will tell us the chemical makeup of the star.
Yeah.
And if we have data before and after it ate a planet, would a planet be big enough to make a difference in the spectroscopy?
Yeah, that's a great question. So the question was, so spectroscopy, looking at the chemical fingerprints of the star, could we tell a difference when if the star has ingested a planet or not? And the answer to that question is that we do have spectroscopy. We did look at the spectroscopy, and the spectroscopy actually looks surprisingly normal. Now, that doesn't mean that a planet ingestion did not happen. And it turns out that the signatures of spectroscopy that we would see of an eaten planet would be noticeable and are most present as a function of time. So like, if I ate a planet today and you tried to figure out if I ate a planet today after like, 20 years or so, you wouldn't be able to tell because all that material has mixed in now with the star. But if that is a fairly recent event, then it might be the case that you might be able to see traces of, that world that you ate. So, in this case, it could have been maybe like a rocky planet or so. So it could be the case. So, folks looked for that. They didn't seem to report any anomalies in the spectroscopy. So does that mean that it didn't eat a planet? A little bit hard to tell. Like, they had some predictions on when this happened, but, no one's exactly entirely sure when that case would have happened. Okay, great. Well, thank you all so much. Before you clap, one quick thing. Where's the laser pointer? Oh, there we go. Okay. Before I let you all go, I just want to quickly mention, not more science. No. Let me see if I can find it.
Like rapid fire.
There's like a planetarium slide. Keep going. Yeah, you see, I had a lot of ambition to talk about a lot of things. Oh, here we go. Great. Yeah, that one. Okay, yeah, I just quickly want to do a shout out for the UW Planetarium. So, part of my, yes, so the planetarium is open. We're back in April. We're going to start accepting again shows. Yes, I am the director of the planetarium. We want all of you to come to the planetarium. Starting in April and May, we'll have public Friday public shows. So you could sign up. Please feel free to check out our Instagram, our Facebook page, and our website. We have all the information there. But we're going to have public shows so you all can come and explore all the wonders of the universe. Okay. Thank you all again. Appreciate it.
quickly announce the trivia answers and the winners, and we're going to have a 5-minute break and come back for the next talk. If you do win trivia, please wait until the end of the second talk to come get your prize. Okay, so quickly through the trivia answers. Betelgeuse is a red supergiant star. Pretty sure Andy said that. It's also a movie star, but thank you guys for understanding what I meant. The radius of Betelgeuse is about 700 times the radius of our sun. O-type stars are much larger than the sun, but they burn out much faster. They're the rock stars of the star world. This is the Tarantula Nebula. If you guessed the Bouquet Nebula, I also guessed that when Sam showed me this question. Okay. The star nicknamed Lucy is in the constellation of Centaurus. The highest redshift JWST has observed is greater than 14, according to, nope. Oh, no, it's good. Okay, I was like, did I get that wrong? Okay, perfect, cool. It was pointed out to me that they're all greater than 6. Thank you for understanding what I meant. Okay, so a total solar eclipse was used to observe gravitational lensing for the first time. An Einstein ring is a specific kind of gravitational lensing that creates a bullseye pattern. JWST is 1 million miles from the Earth. And finally, when a galaxy's light is stretched as it moves away from us, that creates a redshift. Okay, so the winners of the trivia, we have 4 winners who all got 8 questions right. Drum roll. The first winner is your favorite exoplanet. Nice. The next winner is Quinn and Natalie. Woo! The next winner is Titan Uranus. And finally, Bursty Million Years. Nice. Okay, so you can get your prize after the second talk. So we're going to take a quick, around 5-minute intermission right now, and then I'll introduce our next speaker, Gourav Khullar. Did everybody get more beer? Hot dogs? All right, so I'm going to get started. I'm going to bring on the second speaker of the evening. It is my pleasure to introduce Dr. Gourav Khullar. He is a postdoctoral fellow at the University of Washington, and he is interested in star formation in galaxies. So with that, I'd like to bring on Gourav.
Thank you. Thank you so much. Sorry, I almost collided into you there. Okay, can folks hear me at the back? Okay, cool. If you can't, just yell, please. Thank you. So right before this, Andy, who was our super kick-ass speaker before, we were just talking about this, and we were like, who wants to go first, right? Because that was clearly a hard act to follow. And I realized that I like to go first because by this time I'm a little inebriated. But I realized that Andy's talk was going to be all about this super kick-ass physics. Everybody gets to learn a lot because a lot of stuff in this talk is a little bit depressing, especially in the world we live in, which is burning as we speak, right? But I hope there is fun stuff in here as well. There's going to be a lot of rainbows. There's going to be a lot of love. There's going to be gorgeous physics, I promise. There is also going to be light rays that do not like to travel straight, you know. No, sorry. That's fine. I can't swear here, right? Like, I mean, yeah, okay, I can swear. Yeah, okay. Yeah. I mean, light rays are gay as fuck, right? I mean, so I really hope that I can. Nice T-shirt, by the way. Yeah. I hope I can convince you that that is actually happening instead of me just using February as an excuse to spread love and joy in this burning world, right? Okay, anyway, my name is Gourav Khullar. My pronouns are he, him, his. I'm a postdoctoral fellow here. I moved to Seattle 4 months ago. Thankfully, have not seen the Seattle freeze, both literally and metaphorically yet. Please never change. Okay, so what do I work on? I work on galaxies. I like to think of galaxies as some of many components. But at the end of the day, they are basically a bunch of stars, a lot of dust, and really a lot of dark matter. And the idea is to knit a cohesive story to tell what's going on with all of these different components into one gravitational entity, right? Andy talked about stars in our own galaxy, the Milky Way, which in my opinion is the most boring. There's literally nothing exciting going on in the Milky Way, no offense. But you know, you got to study it because you're in it, I guess. But there are trillions and trillions of galaxies out there that we, in all honesty, we've used the Milky Way as a laboratory to learn about these faraway galaxies. And I like to study these super faraway galaxies, right? And the way I do that is using a couple of techniques, photometry and spectroscopy. Photometry is something that I'm sure all of you are familiar with. All of you play with your iPhones and your sepia tones and et cetera, where you selectively register filters or wavelengths and basically try to figure out how much flux there is in those wavelengths or energies or frequencies, right? And so this is my cat, Bella. And I promise Bella is not a white, she's not a black body that she's, you know, radiating at all wavelengths, but this is a really nice example that I'm showing you, plots. But what I'm showing here is basically Bella, which is analogous to like this galaxy, right? And so if you pass her through a bunch of different filters, you only see some wavelengths, some energies, some frequencies. And what that effectively means is that you're seeing specific features of this astronomical object. Yes, she was only partly named after Bellatrix the star. The other was Twilight, and you know. I'm honest enough to admit it. I mean, okay. So, for example, if you have a galaxy like this, really far away system, this is the galaxy that I'll talk about a lot today because it's one of my favorite things in the universe. If you only observe this in the red filter, which is similar to the red filter of your eyes, right? You only see very particular parts of this field of view. If you have an I-band filter, which is an astronomy filter that you see at telescopes, you suddenly start seeing redder things, more detailed things. And then an H-band filter, which is more like a night vision goggle, like H-band. It's like an infrared filter. You basically, in Bella's example, you're seeing, again, very, very different things. And the idea with these kind of photometric observations is you put all this information together, again, to knit a cohesive story about which kind of physics is happening at which wavelengths, and which wavelengths are showing you or demonstrating you processes in different parts of the galaxy, for example. But photometry is not the fun part. I think the fun part is spectroscopy, right? So spectroscopy is essentially the technique of splitting light into its constituent wavelengths, just like photometry, but in a much, much finer way. And at baseline, I'm sure a lot of you are familiar with this, at a very, very basic level, what's basically happening is you're basically putting a prism in front of your telescope. And the prism is splitting light into its constituent wavelengths or energies or frequencies, and you're basically getting something like a continuous spectrum. But a lot more stuff is happening in a galaxy. Bella is not as exciting, right? No offense, Bella. But if there's a hot black body, like a star or a collection of stars, like a galaxy, and the light is passing through a cloud of cooler gas, some of the photons will get absorbed and scattered away, and you'll suddenly start seeing gaps. And that's what we call an absorption line spectrum. But if for some weird reason, you're not directly in the line of sight of the hot black body and the cooler gas in the middle, but you're only looking at the cloud of cooler gas directly, then you don't get this underlying continuous spectrum that this background object is emitting continuously. You're only seeing the scattered off radiation from the missing absorption line spectrum, and that's what we call an emission line spectrum. So astronomers effectively, long story short, see all sorts of spectra when they do this study or this analysis called spectroscopy. And so the way I think about spectroscopy is it's basically a very, very fine way of taking filter imaging. Or the way I think about imaging or photometry is it's very coarse spectroscopy. And so at the end of the day, you're effectively trying to figure out what's going on in a given astronomical object as a function of wavelength of energy. Because different physical processes have different imprints at different wavelengths. That's the end story of the physics of my talk, because after this, it's smooth sailing, I promise. So, why are we excited about this? Because we built amazing telescopes, like Andy mentioned, right? Some really, really amazing facilities that were sent in space. I really, really hope everybody's heard of the Hubble Space Telescope, because if not, I'm very sorry. How many objects do you think are in this image? This is the Hubble Ultra Deep Field. This is one of the most famous pictures that Hubble has ever produced in the last 30, 35 years. Like 500, 1,000? Like 5. Sorry? 5? Did you say 5, Sam? Very close, but not true. 5,000? Who said 5,000? 10,000? You said 5,000? No? Oh, I'm so sorry. Yeah, it's about 9,000. 9 or 10,000. Yeah. And this is the size of a coin, I think. I'm happy to be wrong about this, but I think this is basically approximately the size of a coin if you put the coin as far away from you as possible in your hand. Okay? But now we have a fancy new telescope called JWST, which is actually one of the most amazing things humans ever built. No, I'm kidding. I'm just kidding, Andy. I promise I'm kidding. I'm just kidding. JWST, this is something we launched Christmas year 2021 after 35 years of development. Thousands of astronomers, engineers, scientists came together to build, again, one of the most remarkable things we ever built, the size of a tennis court. This is also approximately the size of 1/10 that of a coin, if you put it really far away from you. The field of a galaxy cluster called Abell 2744. Okay, how many galaxies do you think are in this picture? 10, double the number. Great, Sam. You're getting there, How many folks think like 500? How about 5,000? 10,000. That's great. How many people think 20,000? 20,000. That's awesome. How many of you think a million? Oh, no, million's too much. I mean, I want to be right. I don't want to exaggerate, but It's 100,000. There are 100,000 galaxies in this very picture. They range from galaxies that were observed at an epoch when the universe was 10 billion years old, all the way to when the universe was 500 million years old. And it's one of the most remarkable images that we've seen of a very, very tiny part of the universe. And a lot of my work over the last 2 to 3 years has been about studying galaxies that are red and dead, that don't form stars anymore in the earliest epochs of the universe in this field. I promise you, I cannot point which galaxies I work with. It's just impossible. It's 100,000 galaxies in this picture, right? But let's come a little bit closer, right? Because at the end of the day, the goal is what do we know about the physics of galaxies? So these are, again, JWST images of very, very nearby galaxies. These are catalogs that were created 100 to 150 years ago called the Near Field Galaxy Catalog, I believe. That's what it's called, Nearby Galaxy Catalog. And we've used JWST, especially its infrared capabilities, to complement what we know from Hubble. And combining Hubble and JWST information, we've basically been able to put night vision goggles in front of our eyes and take very, very high resolution images of these galaxies. And the critical thing that I'm very excited about these days, so I would say like maybe 30% of my life is spent thinking about this, is what is actually going on at the heart. Sorry, I'm trying to insert the love theme. What's happening at the heart of star formation in nearby galaxies, right? So I promise this picture looked way different on my laptop, but every single resolved dot that you're seeing here is basically about 10-ish solar systems. And this is the nearby galaxy, right? So don't get me wrong, but it's not a galaxy that we can reach like tomorrow. So it's anywhere between half to 10 times the size of our Milky Way. But each tiny reddish dot that you're seeing is basically a site of star formation. It's a stellar nursery. But again, this is right now, like at redshift 0, which is when the universe is 13.6, 14 billion years old. And these are the reddest observations of these regions, because these red regions are not masking any dust. They're giving us the full picture of where star formation is happening. And these stellar nurseries are really, really at full display for us. But the thing is, again, I've told you, Milky Way is not real. Nearby galaxies are not real. So my goal is, like, can we do this with the first galaxies that have ever been formed? Right? Did someone say no? Someone say no? No? Okay, no. Okay. Yes, we can. All right. So lensing. Lensing is awesome. It's basically a background object is throwing light at us. Light wants to travel in a straight as fuck path. It encounters space-time that has, and the fabric of space-time in this context, thinking about it as fabric of space is probably good. It gets bent by a massive object that is intermediate between us, the observer, and the background object that is sending light towards us. And because light wants to travel in a straight path, the space says no more straight path for you. And so light gets bent, and you can actually look at this. How many of you have non-full glasses with stems? I promise I don't want to make you try doing anything when you have beer in them. But basically, if you finish them off and you use that base of the stem of those glasses towards any of the light sources, you can reproduce gravitational lensing, because the lamps here are basically the background object, the stem is the lens, and your eyes are JWST. So you can actually do this like right now. And so you see arc-like features, like either they're full arcs, depending on where the background source is, where your stem of your glass is. But you also see partial arcs, like you're seeing on the top right corner over there. And so most of my job is to basically look for these lensed systems, right? So again, just to summarize, lensing is about trying to study phenomena where light from background objects gets bent by intermediate massive things. And the manifestation of that is a virtual image of that background source that looks like an arc or looks like a ring. Depends on, again, the orientation of the background object relative to us, how far it is relative to the lens in us, how massive the intermediate thing is. All of these things go into play. All right, how are we feeling about lensing? Good? Sad? Happy? Hopeful? Okay, good. Yeah, yeah. Say no again, please. I'm just kidding. All right. So sometimes you see creepy things like this as well. Yeah. Um, okay, creepy, happy, depending on half glass, empty, half full, whatever. Um, but we know lensing really well for faraway galaxies, right? Each of the yellowish things here is an intermediate galaxy that we've observed with ground-based telescopes. In this case, this is a survey called the Sloan Giant Arc Survey, SGAS. It's a team I've been part of 10 years. And this is from ground-based observations from Gemini. But the first time these objects were seen in an image, an RGB image, we're using the Sloan Digital Sky Survey, the OG survey, right, from the ground. And so every yellowish thing here is part of a galaxy cluster. Galaxy cluster are the most massive things out there, right? Anywhere between 50 or 1,000 to 1,000 galaxies just hanging out together, doing fun things. But they also create a mass sheet effectively. So everything that's in the background, at the right orientation, at the right distance, creates a bluish looking arc. So if the objects are nearby in the yellow, everything that you're seeing here in blue is a background arc that is being lensed. And I just want to say the distortion is not the only effect that lensing does. It also magnifies things, exactly like what my glasses are doing, what half the room's glasses are doing, right? They are magnifying things. Sam, I think for you, the glasses need to magnify more than the double number that you were. Anyway. So every tiny thing here, I think it's very safe to say that if the lensing effect was not happening, the distortion would be weird, sure, like that weirdness would go away, but these would be too faint for us to see otherwise. And so lensing is really doing a magnification effect for the rest of the universe as well. And I showed you a picture of the Abell 2744 cluster with JWST, right? Like half the galaxies that you see over there are lensed. And about 10% of the galaxies will not be seen, especially the ones in the earliest part of the universe. They will not be seen if lensing did not exist as a phenomena. So yet again, Einstein and the cohort of people who were doing really fun things back in the day were right. That general relativity works, its manifestation, gravitational lensing, is a real thing, and this is proof of that. So this is one of my favorite things in the world and universe. I want to talk about this a little bit. This is a galaxy that I helped discover, part of the Cool Lamps collaboration. Obviously, you all are repeat offenders of Astronomy on Tap. You know astronomers are awesome at naming things, right? So Cool Lamps was an organization, collaboration, a survey that I helped co-found when I was in grad school. It stands for, it's very obvious, Chicago, that's the first O. Optically selected, that's the second O. Lenses, that's cool. Located at the margins of public surveys. Anyway, so dumb. Okay, Cool Lamps is amazing because it's basically a team that my PhD advisor and I co-founded. That's 99% undergraduate students at the University of Chicago. And the idea is for them to use a whole quarter, just like the University of Washington system. They spend a whole quarter learning about galaxies, lensing, the world, the friends we made along the way. And then they basically design an observing program on using observations from the Magellan telescopes, which are in Chile, to do science. And this program was mostly designed around public surveys that have not been very well studied yet. And these public surveys, in this case, was a survey called the DCAL survey. And a lot of the Cool Lamps work that we did in 2020 and 2021 was around looking, visually inspecting, lensing candidates in decals. And this is one of the most extraordinary things we found. It's approximately the mass of the Milky Way, but it's really far away. It's basically at redshift 5 when the universe was only 1 billion years old. And the thing that we care about is not the yellowy patch in the middle, it's the arc, right? And that arc is the thing that is gravitationally lensed. And the only reason we are seeing this at such far distance, but we're still seeing it from the ground, is because it's magnified about 70 times by this intermediate object in the yellow. Oh, sorry. Yeah, it's also called the Quasar. So Disney, please don't sue us. But apparently they're really good at suing people for no fucking reason. But we're calling it the WAS-ARC because of obvious reasons, the whole like Cyclops situation. But the WAS-ARC is fantastic. Like it's teaching us a lot about the inner workings of galaxies in the early universe, especially like we call it the cosmic dawn, the first billion years of the universe. And this is what this galaxy looks like with JWST. This is ground-based. This is JWST. And each of those clumpy things that you're seeing over there, and this is the bread and butter of sort of my being here, is approximately 20 to 100 solar system wide regions. So imagine the first billion years, you're basically looking at stellar nurseries. And the most amazing part about this is that every pixel in this image that you're seeing, we have a spectrum for it because JWST has those capabilities. It's called an integral field spectrograph, an IFS, and these are called IFU observations. So every time you see the word IFU in your spare time, you're basically seeing every pixel is a spectrum, which means we have very detailed information about every single region here. So what I was talking about, the Milky Way does not exist, stellar nurseries, we can now do this kind of work with JWST in the earliest part of the universe. And this makes a really badass tattoo. And I'm sorry, I don't want to take my clothes off, but anyway. Anybody who wants a fill-in tattoo, please come talk to me because it hurts like a. But it looks really good. It looks very good. I've been thinking about this for like since the day I wrote this paper. I was like, I want to do this, and I finally did it. 8 weeks ago, 10 weeks ago. Yeah. Okay. Enough about me. Have you noticed anything wonky about this talk? Talk about Hubble, named after Edwin Hubble. We talk about JWST. We talk about weird cats and tattoos and rainbows. Like, have people felt weird things? Something weird going on in this talk. You all came to hear about JWST, and I'm just wondering if that request and excitement has been satiated.
Take it off.
I really thought it was a PG audience. Anyway, okay. I think one of the things that I think on purpose left out was we've not talked about like why we named the telescope JWST. Like why is this an exciting thing at all? And it's on purpose. The community as a collective has decided not to call this telescope, which again is one of the most amazing things humans have ever created. It's a marvel of engineering, a marvel of science and technology. Could not have happened without the collaboration of thousands of astronomers, scientists, countries came together to build this telescope and send it into space in a way where the spacecraft that was designed was so efficient that it didn't require the fuel it needed to reach where it wanted to reach. So now the lifetime was extended 5 times. That's how amazing we are at what we do when we come together as a team, but nobody wants to talk about this telescope by its full name. And the reason for that is that it's named after a homophobic bigot. The person's name is James Webb. James Webb was director of NASA during a nostalgic time in this country when we were winning the Cold War by declaring that going to the moon was the most important thing that humankind was capable of doing. And so in the 80s, when new telescopes were being designed, we were winning the Cold War, but we still wanted to do more, use the military-industrial complex to justify our scientific enterprise. An outcome, an offshoot of that was new telescopes in space. And a random senator who was head of the science committee in the late 80s, early 90s, decided that a tribute to James Webb would be the right way to go because this telescope will take 20 to 30 years to build and nobody cares about gay folks. James Webb was part of the Senate discussions that kickstarted the lavender scare in the 50s and 60s. How many of you are familiar with the lavender scare? It was a systematic purge of LGBTQ folks from the federal government and any organization and institution and framework that relied on the federal government funding. And this systematic purge basically cost people their lives, their livelihood, their whole enterprises. And we named this after the person who was in charge of doing this purge at NASA in the 50s and 60s. There are written records that show this. Um, Again, I just want to emphasize that naming a telescope is its own thing, but this telescope was named much before any of the first mirrors were built, the first instruments were built. And the lavender scare's shadow was always around, but this movement really gathered steam to recognize the problem with naming this telescope after James Webb about a couple of years before the telescope was launched in 2021. There was a very grassroots movement from astronomers who are now using the telescope, but also didn't use the telescope as part of community organizing within astronomy, both in North America but also internationally, that the James Webb Space Telescope needs to be renamed. And this movement gathered so much steam that NASA had to, and this is folks at Goddard specifically, this is NASA Goddard Space Flight Center in Maryland. Folks at NASA Goddard were explicitly requested and pressurized into forming committees that try to review historical records. And they came to the conclusion that he wasn't homophobic or directly responsible for the firing of any other person because they recognized that tacit complicity, only active complicity was important, not tacit complicity. And I think the thing that I want to say is that like astronomers and scientists and good scientists, we want to evaluate everything that our community puts out. And again, a cohort of our peers came together to review that very report that NASA put out and basically proved that it was deeply unscientific and riddled with holes and used selective facts and methodologies to exonerate a person who's been dead for years, right? And I think the question that I want to definitely ask you all at the end of this talk, I only have a couple more slides left, is one, what does it mean to name something after someone who, we think did good things related to the Apollo program and we need to honor them in some capacity? And what does it mean to not name something after a human being who in a position of power was responsible for affecting the lives of the most marginalized people in our communities? And what does that say about who gets to do astronomy today? So just keep these questions in your mind when you're asking me questions so that we can have a conversation about it. Because these are, again, topics and questions that are not only, I think, important to me at my heart, but I think are coming up more and more in the last couple of weeks as people are, again, losing their livelihoods for participating in community organizing and social justice work, right? So what are we doing about this, right? I think symbols are important. They're not the only thing, but they are a small cog in the bigger picture. So here's Bella. She's back. Bella is here to demonstrate that the one example that I showed you of the WAS arc is, again, one example. Now we have surveys of such lens galaxies that allow us to study galaxies at cosmic noon, cosmic dawn, but again, study them in a spatially resolved manner, which means we're still studying regions that are a few solar systems wide so that we can say something about the buildup of the entire galaxy by virtue of putting together these tiny clumpy regions. And so me and a couple of my colleagues came together and asked for observations on JWST. I almost said the name again. And we came together to answer this exact question. Can we put together clumpy regions at cosmic noon and cosmic dawn, like the earliest epochs of the universe, but can we do this in a systematic manner? And now we can with a new survey that we've created called LEGOS. Again, awesome name, right? Lensing and galaxy growth, observing substructures. Because exactly like LEGOS, we're basically putting galaxies together by virtue of using individual clumpy regions of these lens galaxies together. So you can think about this new survey, and you should expect papers from our group very soon. What's basically happening is we're thinking about these not as a collection of galaxies, but a collection of hundreds of clumps, right? And these clumps are all 20, 30, 50, 100 solar systems wide, and they all come together to form these galaxies as we know today. So it's great to study them in the past so we can say something about galaxies today, right? And you can see the rainbow symbology is actually very particular. The Philly Pride flag is now becoming a very, very major part of the symbology around pushing back against homophobic narratives within astronomy. And you see this in many, many different surveys, including LEGOS, right? And there are folks who are very much excited about organizing around this issue, which is like who gets to do science, who gets to name the people we honor, right? And why are we honoring these specific people? Why are we holding people to standards from X time in Y time? Like those questions come up as well. Journals are taking note of the fact that community members will not write papers unless they feel comfortable doing so. So there are journals that allow you to, for example, never spell out JWST. So currently I'm putting together a couple of papers. I'd never fully write the name JWST. Like it's always the acronym. And that's professionally allowed, which is kind of exciting. So this is my last slide. I just want to quote something from the 2021 article that I showed you here. The James Webb Space Telescope needs to be renamed. And I just want to read it out loud because it's just really beautiful words that I will not be able to do justice paraphrasing. James Webb's legacy is the antithesis of the dreaming and sense of freedom, inspired by the exploration of deep time and distant space. There will always be complications in naming monuments or facilities after individuals. Yet we can honor the incredible heroes who work tirelessly to liberate others. We should name telescopes out of love for those who came before us and led the way to freedom, and out of love for those who are coming up after. This is an article written by Professors Prescott Weinstein, Professor Sarah Tuttle, who's at the University of Washington, Lucien Valkovich, and Dr. Brian Nord in 2021 in a Scientific American article. I highly encourage you to check it out. They're beautiful, beautiful words. Before I end, I just want to say again, right? I've said this like 20 times now. This telescope is a masterpiece of human invention and innovation. Every single thing that I've done over the last 10 years in my career, has been me being like part of like a cog of a bigger wheel, because collaborations are what's running astronomy today. We love valorizing individual people. Like, don't get me wrong, it's a storytelling problem, right? Like Richard Feynman is one of the most famous physicists. He's a jackass and a bigot and an incredible creep. And the fallacy of the lone genius is that you often tend to ignore their grayish or bad side. And this has happened across history. This is not new to astronomy. But what that's happened is, in the recent times, it's discouraged people from writing about the teams that are putting all of this work to create beautiful, beautiful things. And not just the people who are building these telescopes, but also people who are using the telescopes, right? Every year, people from all over the world apply for time, requesting observations of their favorite samples of objects, the furthest galaxies, the most amazing supernovae, like the most amazing variable stars, like Andy was telling us about. And they want to use JWST, but how do we use a telescope whose running and the creation was marred by people making unilateral decisions, not on behalf of the people who wanted to use them, but on behalf of political gains? So I just want to say that I think the telescope is for all, astronomy is for all, and these are generic things to say. Like, there are other things happening, I'm happy to talk about it. But JWST is clearly, the community is a testament to the fact that this telescope is for all, and astronomy is for all. And really, just fuck homophobia and transphobia. Thank you. Questions?
I'd like to answer one of your earlier questions, like kind of the balance between someone's good scientific contributions and then like their morality. Going back to James Webb specifically, he hindered the scientific process as well, blind firing all those people. So he was hindering both things instead of just like bringing up one and like, because the balance isn't really between the two. It's both of them are affected.
I think that's a great point. So, folks in the back, James Webb was actively complicit in firing people and hindering the scientific process. And I feel like a lot of people agree with you, and a lot of people don't. I think I came to this country like, what, 11 years ago, 10 years ago? And one of the things that I found in the professional setting here was how interesting it is that all our structures are built around individualistic responsibility. And that's why people fail to see the power dynamics that exist fundamentally in the director of NASA even if not having any proof of actively doing bad things, being complicit in a systemic erasure of people who are working at NASA, right?
He had the power to prevent that.
I wish more people saw those power dynamics. Yeah, that's a great point. Other questions? Yeah. Behind you, Ishan, if that's okay. Please go for it.
Sure. Are you able to infer the shape of other galaxies from the gravitational lensing? Because it's been smeared out, but put it back together hydrophobically?
That is a great question. So the question is, can we sort of reconstruct the true shape of the background galaxy once it's been smeared by lensing? Is that accurate? Yes, we can. Because the mathematical construct of lensing allows us to build computational models that tell us exactly what the lens could have potentially done to this background galaxy. So we backtrack it. And so we're getting very good at doing this, even for complex mass sheets that are intermediate between the background galaxy and us. It's an uncertain process, like any modeling in astronomy, but we're getting very, very good at it. Sean?
So about the time JWST was launching, the petition went around to rename JWST. And about the same time, there was also warning that some people were making a warning or concern that by signing the petition, people on that list would be targeted in terms of being deprioritized for funding from NASA and federal government going forward. Does that concern panned out to be true?
No, it did not. It did not. There was definitely concern during the time when this petition was launching that there would be financial ramifications for folks who were participating in the rename JWST movement. But the process of receiving funding from NASA is convoluted and complex and peer-reviewed enough that didn't, thankfully did not pan out to be true. Yes?
Did the spectroscopy of that 13 billion year old stellar nursery show anything interesting?
Yes, yes. The spectroscopy of that galaxy, the WAS-ARC, effectively showed us that overall the galaxy is what we are now calling a napping galaxy. So it's a galaxy that formed a bunch of stars, maybe 999 million years before we observed it. And yeah, sorry, 999 million years after the Big Bang. But then in the last 5 to 10 million years between the star formation happening and us observing it at redshift 5, it plummeted. So it's something that we call a post-starburst galaxy. It's one of the highest redshift, the earliest post-starburst galaxies we've ever discovered. And the funny thing is that even though that's the overall picture of the galaxy, there is still clumpy regions in the system that the spectroscopy is showing us are still actively forming stars. So there's a patchy way in which the galaxy is stopping to form stars instead of all at once. And again, lensing and space telescopes are the only combination that will let you make this kind of analysis. Because without lensing, you only see blobs at these distances. Does that answer your question? Yes.
Like observing a galaxy that's so similar to the Milky Way so early in the evolution, is that expected?
No. Yeah, no. We do expect massive things in the early universe now. You may have seen articles about the first results from JWST showing really, really massive things. Some of them turned out to be a bad attribution of light to weight or mass. So we thought they were more massive, but they're really not. Some of them are still massive, but within the confines of what we think theoretically is possible. But I will say this, though, that I think even though for that one particular galaxy, we were surprised to see a massive system like that, we are seeing samples of those with JWST now because we have more wavelengths to attack, which means that we can have a more holistic picture of the stellar mass of the galaxy.
Is that still like compatible with the lambda CDM model?
It is. It is. If anyone's telling you something's wrong with lambda CDM, throw rocks at them. All right. One question, two more? Two more questions. Yes.
Thank you for discussing the issue with JWST and the naming, and obviously there's a lot of parallels to our current time. And I just imagine it's been a very stressful time. What can normies like us do to help out astronomy programs and things like that in academia?
Are you part of a union? Join your workplace union. That's definitely number one. But in all, I mean, that's my default answer to everything these days. Yeah, I mean, I feel like I'm a normie too because honestly, doing astronomy at this time seems so silly. Like I don't know. There are a lot of astronomers in the room. Again, that's why I wanted to go second, Andy, because I'm such a depressor. Yeah, I'll be honest. Your question is really hitting the crux of both why I wanted to give this talk, but also why I wanted to go second, which is that, yeah, the world's burning, and it just seems really stupid to be doing astronomy this time. I'll be very honest, right? At the same time, it's been known to me and my fellow peers who are putting together an amazing show with Astronomy on Tap that this is such an incredible source of joy, as is so many other things, right? And I think that anything that is bringing you joy, like that cannot be removed from your life at this point. But the most important thing, which is the answer to your question, I promise I'm coming to it, which is that you got to organize. Organize, organize, organize. I think folks that are doing bad things right now, namely the fascists that control the federal government, are relying on one, your apathy, two, something that's called the shock doctrine, which is you do 20,000 bad things together so that you don't have the energy to fight all of them at once. And three, they just want you to be complicit somehow, right? Just don't let them do any of those three things. Focus your energy on organizing things and get back at it. In terms of academic help, I think one of the things that we are heavily relying on is, I'm not going to say write to your representatives, please. Like, Pramila Jaipal is a representative here in this district. She's awesome. You don't need to, like, also, I'm sorry, democracy is a farce, right? But I think one of the most important things that you can do is support petitions, go to rallies, specifically around funding freezes in academia, and a lot of them are happening in Seattle. I think this is a great place to get involved in that practice. I would also say participate in citizen science projects. I think that's also a very, very great way of bridging the gap between what you're referring to as normies and folks who are excited about doing PhDs. Because I think that gap is very fictitious, and I think that needs to be bridged because astronomy is a brilliant gateway to talking about the sociological aspects of how we think about the world, right? So I hope that kind of answers your question. I don't have all the answers, I'm sorry. One question, last question. No more questions. All right, I think we're at it.
Thank you. Thank you so much. All right, let's give another big round of applause for both of our speakers of the evening. All right, and before we get going for the night, I need you all to help indulge me on something, namely embarrassing my friends, which is like one of my favorite things in the entire world. So, as you guys know, Sam Garza, Sam, why don't you stand up? It's her birthday tonight. So I thought that we could all sing for her. All right. Happy birthday to you. Happy birthday to you. Happy birthday, dear Sam. Happy birthday to you. Are you one? Are you two? No, I'm just kidding. Okay. And in the name of appreciating Sam, Sam does all the social media posts, and she does a fantastic job. She's the only reason any of us are here tonight, realistically. And next month, I will be traveling to give some talks, so Sam will be filling in as MC for me in March, which brings me to my final point of this monologue, which is that the next Astronomy on Tap will be on March 26th. at 7 p.m. Please show up. All right, so with that, I'll release you. Thank you all so much for coming, and please get home safe. Oh, and if you won trivia, come get your trivia.